Welcome to the Random Interaction Seminar. Today's speaker is Arindam Pramanik from TIFR. He is a PhD student who is working with Professor Kalabaran Maiti in DC MPMS. And Arindam will tell us today about his studies on Dirac electrons in BIPD and graphene using ARPES. So Arindam, you can start.
Okay, sir, thank you. Oh. Okay, so in this talk, I am going to show our ARPES results on BIPD and graphene. So first, I will start with a general introduction, and then I will introduce some basic ideas of the angle resolved photoemission technique. Then I will show our results on BIPD and graphene. So, and basically what we did was the study of these Dirac electrons of BIPD and graphene. So graphene, we know that it has a conical band structure and it has been well studied, and BIPD also has been well studied, and it has these Dirac-like surface states. So we basically studied those things again using the angle resolved photoemission technique. And this angle resolved photoemission technique is particularly useful for these kinds of studies because it can directly map the band structure. So the effect of crystal symmetries on the band structure and also the many body interaction induced effects in the band structure can be proved very easily, that I will show. And examples of these, that effect of crystal symmetries and many body interaction effects, we will also get to see those things in the studies of BIPD and graphene. And already there are lots of ARPES paper published on these two systems, but I will show that there are still few questions which remains to be answered. So we actually tried to address some of those issues, and I will show, some of those studies. So I will first start with the basic of the photoemission technique. So photoemission technique is based on photoelectric effect. So we shine light on a sample solid system, and if the energy of the photon is high enough, then the electrons from the system can come out. So this is a schematics of that photoemission process. So this axis is this is the density of states of the solid system. This axis is the your number of electrons, and this is the energy axis. So this is inside the system. So you can see there are two reference labels actually we use for these studies. So one is the Fermi energy, that is EF. So energy of the electrons when it is inside the system is given with respect to this Fermi level. So basically, and the other reference level is E vacuum. So the energy of the photoelectrons when it comes out of the system, so that energy is given with respect to this vacuum level, and the energy difference between these two levels is phi, which is the work function. So if I have a system which has this density of states, then in photoemission we get this kind of spectrum. So now this axis has become now the kinetic energy, and this axis is your total number of electrons. So if you take a particular core level here, so these are the core electrons which lie far away from the Fermi level, and this is the valence electrons. These are the valence electrons. So now if you take one core level and see, so you can see that, this electron, if it has to come out of the system, then it has to spend some amount of energy. And that expenditure has two components. One is the binding energy. So first it has to go to the Fermi level. So that much amount of energy is it has to spend. So that is equal to the binding energy. And then again to come out of the system, it has to spend this amount of energy equal to the work function. So basically there are two components in this expenditure. And the rest of the energy is manifested as kinetic energy, which is given with respect to this vacuum level. So basically the kinetic energy is the photon energy minus these two expenditures. So one is this work function and another is binding energy. So now depending on the kinds of excitation source we are using, this particular technique, photoemission technique, goes by many names. So if we use the X-ray photons, then it is known as X-ray photon emission spectroscopy, or XPS in short. Or if we use the ultraviolet photons, then it is known as UPS, or ultraviolet photon emission spectroscopy. And in the conventional photon emission spectrum, so what we measure is that how many electrons are there in a particular kinetic energy interval. So basically it gives us the density of states information about the system directly. We do not measure the angle of emission, that is the momentum information of the electrons. So in conventional photon emission, we measure the density of states of the system. But with the advent of new detectors, we can measure both the energy and the momentum of the outgoing electrons. And from there, we can find out the band structure, the entire band structure, the energy versus momentum plot. So this is a basic model of photo emission technique. This is the primitive model, and it works very well. Also, this is known as the three-step model. So using this model, the entire photo emission process can be seen as 3 steps in this model. So that's why it's called 3-step model. So the Z greater than 0. So this part is the vacuum, and Z less than 0. So this is the solid. Now, before the photo emission happens, before the photon falls on the system, the electron is in this state. So it has energy EI and momentum Ki. I stands for the initial. So this is the initial energy and momentum of the electron. And in the first step, it absorbs the photon and goes to a state where it has momentum and energy, Kf and Df. F stands for final. So this is the first step, which is known as optical excitation of electron. And in the second step, so this excited electron traverses the whole bulk of the material and goes to the surface. So the travel to the surface, that's the second step. And the third step is the transmission through the surface. And now at the surface, because of this termination, electric field exists at the surface, which is perpendicular to the surface. So that changes the energy and momentum of the electron. So when it goes to the escapes to the vacuum, it acquires new momentum and new energy, which is given here as kV and EV, that is in the vacuum. So now in experiments, we measure these two quantities, and from there we try to find out these quantities. kV, EV are measured, and we want to find out the Ki, EI. Now I will show that using some geometrical ideas. The photo emission geometry and some conservation rules. If we know these quantities, then we will get to know these quantities. So this is the basic geometry of the ARPES. So this is the hemispherical analyzer. This is the lens axis system. This is the detector system. And the sample is placed in front of this lens axis. The photon falls on it and the electron comes out of the sample. So here we have to remember that this detector system doesn't directly give us the momentum of the electron. It gives us the angle of emission. So these axes, the black arrow, so that is the Z axis, that is the sample normal. And these two in-plane axes are X and Y. So when the electron comes out of the system, so it makes some angle with the sample normal, that is with the Z axis. This is called theta. And here, this slit axis, the slit is parallel to the Y axis. So if any electron which has a Y momentum, it will be able to go through this slit. But if any electron which has X momentum, so it won't be able to go through this slit. So basically in this arrangement, we are basically probing the band structure along this momentum axis, along Y axis. So if you want to measure the momentum along X axis, then you have to tilt the sample. That means you have to rotate the sample with respect to Y axis, so that you intercept those electrons which have some X axis X momentum. So that is called tilt mapping, and we use it extensively to map out the entire band structure of the solid.
Arindam, any electron will have both Y and X component, right? So you are only measuring the Y component?
No, the electrons which are going along the Y axis only, so they cannot have any X momentum. So these are 3 independent components, X, Y, and Z.
Okay.
So basically X can be 0 and Y can be non-zero. So basically those 2 are independent components. So like if you plot the band structure, when we plot the band structure, we plot it along a gamma to M or gamma to K. So that means the electrons have momentum only along gamma m direction or along gamma k direction. Like if you see, I mean the two-dimensional.
Arindam, I guess the question that Tridib is trying to ask is whether you are measuring the projection of the momentum or you are only measuring those electrons which have y momentum and x momentum 0.
Oh, okay. So actually, sir, that depends. So if you use this tilt angle variation, if you use it, then you also get to, actually we are measuring the y-axis momentum. I mean, if the electron has non-zero x momentum, that also we can measure. I mean, the projection actually we measure. So basically,
is that true?
Yes, that I will show later. So using that we measure the whole band structure. So that I will show.
Just 1 second, but I thought your slit is in real space. So if you are moving along x, you will get out of that slit.
No, so actually in that case, we have to tilt. You just rotate the sample. So that rotate the sample about y-axis by, let's say, some angle beta. Then the electrons that are coming along x-axis with angle beta, they will be able to enter the slit.
No, that I understand. But given a particular arrangement or current arrangement, the question is, are you measuring electrons which only have ky and kx equal to 0? Or are you measuring electrons which are going in any direction? You're just measuring their ky component.
Okay, I got the question. So that is actually hard to say unless you perform the entire imaging. You have to do the entire imaging and then you have to compare with the band structure. Exactly what momentum direction are you measuring? So it can be.
Suppose I know that this is my arrangement. Y is exactly in the direction in which you have drawn the figure. Okay. Don't think of changing that. Now the question is, suppose I have an electron which is moving at 45 degrees in the x-ray. Will I measure it in this configuration?
In this configuration, no, you won't be able to measure. But actually what we do is that first we arrange the sample. I mean, the sample is not randomly put there. So if you want to measure along gamma m direction, then we put the sample in such a way that gamma m is along y-axis.
Arindam, you are unnecessarily confusing it. So the question as I'm asking is, given the current orientation, are you going to measure things which are going at 45 degrees? Yes or no? No. So you only measure things which have a momentum along the slit direction.
Yes, exactly.
Now that direction you can change by changing the sample. That's it.
By changing the sample. Okay. So basically using this arrangement, we measure the energy of the electron and the emission angle of this theta. So once we have the energy, so using the dispersion relation, so now we know the energy of the electron in the vacuum, that is EV. So using this dispersion relation, we can get the momentum. So this is the momentum and it now has two components. The momentum now has two components. One is along y direction and another is along z direction. So the y component is given by the sine theta, kV sine theta, and the z component is the cos theta. So basically if you see this figure, now we have this momentum. We know this energy and this momentum and we want to find out this. So there is one intermediate step. So if I know these momentums, then I also get to know these momentums. So because I mean when this is the momentum of the electron before it leaves the surface. So while it leaves the surface, the parallel component of the momentum, the component parallel to the surface, that remains actually conserved because the electric field is perpendicular. So from there we can see that y component, so that is the surface parallel component. So y component in the vacuum and the y component inside the sample. So those two are equal. So that is the kV sine theta. And the perpendicular component is given by this formula. So there
is the electric field is perpendicular to the surface. That's why it would not affect the other components. Is that the reason?
I couldn't hear you properly. Sorry.
The fact that the ky components did not change, is it because the field on the surface is perpendicular?
Yes, yes, yes.
Okay.
Yes. So but the perpendicular component will not remain conserved, so it changes. So there is, I mean, we can find it out by putting a parameter here V naught. So to find out the V naught, we have to do the experiments at various photon energies, and from there we have to find out the V naught. So we won't be requiring this momentum component Kz, because we will be studying the two-dimensional Dirac electrons. So basically only this momentum, the in-plane momentum, this relation will be used, and this won't be required. So now we have these two momentums inside the sample. So the final momentum Kf, it has two components, y and z. We know these two components, and these can be easily found out because these two are related by your reciprocal lattice vector. So once we know this, we'll get to know this. So this is the so these are the basically the geometrical concepts of this thing. So using these relations, so once we have a spectrum using this relation, we can map it to the band structure, map the band structure. But in this ARPES technique, what we measure is the total current of the system, the photocurrent of the system. So the photocurrent is measured basically as a function of your electron momentum and the energy, kinetic energy. So it has three components. So this is your single particle excitation, single particle matrix element. This is the Fermi-Dirac distribution, and this is the spectral function. So this one has the temperature dependence in it. So, and this one is the spectral function, which has the effects of the many body. It has the effects of the many body inside it. So it is given by this formula. So this sigma double dashed, it is the it is your imaginary component of the electron self energy, and sigma dashed is the real component of the self energy.
So,
Now,
Arindam, one question. This is what you would normally call the impulse approximation, right?
The sudden approximation, yes, yes.
So, but this ignores the fact that while traveling to the surface, the electron could have interacted with
Yes,
other.
yes. I mean, it's instantaneous.
So, what kind of energies where this will make sense?
So this one, if you have the electron, kinetic energy of the electron is less. I mean, it takes some time to come out of the system. I mean, if you are doing experiments with very high energies, very high photon energies. Mm-hmm. So in that case, I mean, electron instantaneously comes out of the system. So basically sorry?
So high photon energy.
High photon energies. So at low photon energies, you have to consider this this particular thing.
Just a related question which I did not understand is that why only a single photon is getting absorbed? Is it the answer related to what you say?
No, I mean, we are showering photon on the system, and all the electrons, they are absorbing the photon. But one electron.
So before exiting the system, could it happen that two photons get absorbed?
I think those processes are probably very less probable. I mean, absorbing two photons. Hello?
Yeah.
So I said that, I mean, probably absorbing multiple photons is less probable.
So when you were inferring the first energy level, you were assuming that probabilistically there is only a single photon which
yes.
Statistically, so the energy level that you infer will have just the kind of the most probable energy level.
Exactly. So it will absorb a single, and I think that also depends on the density of the photons, I guess. So if the photon density is very high, probably there would be chances of absorbing 2 or 3 photons is higher, probably.
Okay, thank you.
Photon flux is low, right?
Here photon flux is low.
Okay.
So that answers yes.
Okay. So now, now a resonance happens in this quantity, or this quantity becomes maximum when this becomes 0. So this is So this is your bare electron dispersion when there is no many body interaction. So now this quantity, we see a resonance in this quantity, or this quantity becomes maximum when this becomes 0. So basically for a particular k and omega, if this quantity becomes 0 and it becomes maximum, we say that a quasi-particle of that momentum and energy resides in the system. I mean, I have created a quasi-particle of that momentum and energy in the system. But it can also happen that this, for a given k, I can have multiple resonances, and for a given k, this quantity can become 0 for multiple omegas. So in that case, the extra the resonances that we are getting, so those are called as the new, that signifies the emergence of new quasi-particles in the system with well-defined momentum. So we will see one example of this in the graphene case in the form of plasmaron. So with these basic ideas of photon emission, I will start describing our own work. So our first work was on BIPD. So this is so BIPD is a superconductor with a Tc of 3.8 Kelvin. It's a non-centrosymmetric. It below 483 Kelvin. It assumes a non-centrosymmetric structure, monoclinic structure. So and it also has Dirac states on the surface. So initially it garnered some attention for being a potential candidate for intrinsic topological superconductor. But the ARPACE studies found that these topological surface states, they lie far below the Fermi level. So basically they won't be able to, the surface states won't be able to participate in the superconductivity. So they are not suitable for being a topological superconductor. But anyway, the ARPACE studies continued, and they actually focused on characterizing these particular surface states. So various reports came out, but there were some contradictory results. So I'll show, I mean, say what are those results and where were the confusions. So one confusion was over the momentum space location of these surface states in the Brillouin zone. So, I mean, some of the groups are claiming that it's at the center of the surface Brillouin zone, that is at the gamma bar point, and few were claiming that it's at the edge of the Brillouin zone, that is at S bar point. So that is one confusion, and another confusion was the dimensionality of these Dirac states. Theoretically, I mean, from the DFT calculations, it was shown that these are actually surface states, so they are actually two-dimensional. But experimental verification was not easy, and there was one group which tried to find out the dimensionality, and they reported, I mean, huge deviation from two-dimensionality of these bands. So that is one thing, and there was some anomalous things in there, that deviation. I will show that. And there was also the anisotropic nature of these Dirac states. So anisotropy was there, and it was well known from all these studies. But because of the poor resolutions of the earlier studies, so people did not study this anisotropic nature further. So out of these three issues, I mean, this one was settled, this confusion over the momentum space location. So later band structure studies and also the ARPACE studies, they confirmed that these surface states actually occur at the S bar point. So that is at the edge of the Brillouin zone, not at the gamma bar point. So this is the crystal structure of BIPD. So this is the long axis B, and this is the preferential cleaving plane. So as we know that, I mean, for ARPACE we need clean surfaces of the sample.
Unmesh had a question. Unmesh, you raised your hand. Yeah, go ahead.
No, I think he's going to show this gamma bar and S bar. I was
okay.
It's okay.
Okay, I'll show. Yeah. So this is the crystal structure of BIPD. This is the long axis. So this is also the preferential cleaving plane. So, and ARPACE requires clean surface. So we have to mount the sample in such a way that B axis is out of plane. So when we cleave the sample, it breaks somewhere here. So it gives us it exposes a clean surface. And and during this cleaving, after this cleaving, you can get 0, 1 bar, since it is aligned along B axis, you can get 0, 1, 0 or 0, 1 bar 0 surface. And these two surfaces are not equivalent because of the non-centrosymmetry. And you can see these are the Brillouin zones here. So earlier I talked about the gamma bar point. This is at the center of the Brillouin zone, and this is the surface Brillouin zone, and this is the S bar point. So this is at the edge of the Brillouin zone. So here the Dirac surfaces lie here, this S bar point. And these are the two characteristics spectra of this BIPD. So this spectra, the D is taken along this line. It is taken along this line, and this one is taken along this. So you can see they look very different. So anisotropic nature is very clear, and also that the Dirac node lies far below the Fermi level. It's at 0.66 eV below the Fermi level.
Sorry, can you just show which directions you will show?
Okay, so this D, figure D, it is along this direction.
Okay. And that one is gamma to S bar?
Gamma to S. This is the direction.
I see. And your claim is that this is way below 0, the Dirac point.
Dirac point here lies at 0.66 eV, below the Fermi level.
And why do we see two kind of states in the E?
First, this one.
E, yeah.
Oh, these are the bulk states.
I see.
These are not surface.
I see. And even on the surface state, the one that you have drawn as a point.
So these are the surface states.
Yeah. So, but it just it doesn't look simply like a Dirac point. It bends back and does all sorts of things. So that's what I was going to ask.
Yes. I mean, there is huge anisotropy in this system. So along one direction, they actually merge with the bulk band. In this direction, you can see they merge with the bulk band. But in other direction, that is in this direction, so they merge on itself.
Okay.
So now we'll probe the dimensionality of this Dirac states. So experimentally, to probe the dimensionality, what we do is that we take the same spectrum at various photon energies. So various photon energies only means, and if we take the same spectrum at various photon energies, that means we are taking that spectrum at various kz values, the kz momentum. Because earlier I showed this relation, the kz is related to the kinetic energy. This is the kinetic energy of the electron. So the photon, I mean, that depends on the photon energy. So if we change the photon energy, the kz changes. So basically, acquiring the spectrum at different photon energy means we are acquiring the spectrum at different kz values. So now, and if the state is two-dimensional, then the spectrum should be identical in all the photon energies, because there would be no dependence on kz values. So basically, there would be no dependence on the photon energy, except that the intensity might change because of the matrix element effect. Otherwise, if we plot the dispersion, I mean, in every photon energy, they should look same. And if there is some deviation, if the spectrum changes with the photon energy, then we can say probably there is some three-dimensionality in the system. So we'll see here what happens. So this is one set of spectrum, and this is another set of spectrum, this lower panel. So this above setup in the first set, so we actually optimize the sample at 74 eV. So you can see the Dirac node is clearly seen. And now as we lower the photon energy at 55 eV, you can see there is a little bit of gap opening is there. And at 42 eV, the gap is even higher. So that can be clearly seen in these three panels. So this panel is 40, which corresponds to 42 eV. This is the EDC spectrum of the 42 eV ARPE spectra. So basically, this is the discretized version of that. You can see, so this blue line here, so it is taken at this point. So basically, you can see there, you can fit it with two peaks with a gap in between. So basically, there is a gap there. And this one, you can see there is a single peak. If you take a spectrum, I mean, if you take a cut through this point, there is a single peak. So basically, there is no gap there.
One question though, why would the gap open up when you lower your photon energy? So that means
So that I
KZ, no? I mean, I would have expected it to open up at a higher KZ because there's some whatever KZ squared dependent.
that I will come to it. I mean, how this gap opens up if we change the photon energy. So that actually happens. All these things happens because there is no three-dimensionality in the system. This actually happens because because of the misalignments of the system. I mean, this is an experimental artifact that I will show. So this is another set of spectrum. So here the sample was optimized at the lower photon energy at 35 eV. So you can see a Dirac node here. There is no gap, and the corresponding EDC is here. So you can see you can fit it with a single peak. And now as we increase the photon energy, the gap is increasing. You can see the gap at the node is increasing. At 85 eV, there is a huge gap. And see the corresponding EDC here. You can fit it with two peaks with a huge gap in between. So basically, these two sets have different gap trends. In the first set, as you increase the photon energy, the gap decreases. And in the second set, as you increase the photon energy, the gap increases. So these gap trends we have plotted, you can see. So in the first set, the gap decreases with photon energy. And in the second set, the gap increases. Now using and now if you take it as a face value, then one is tempted to say that, okay, since it is the dispersion is changing, because the spectrum looks different at different photon energies, so probably there is some three-dimensionality. But that is not true, because going from 40 eV, it starts from 25 eV actually, 25, 30 eV. So going from 30 eV to almost 100 eV, so we have actually surpassed 3 Brillouin zones there. So I mean, the band structure, since it has a periodicity over the Brillouin zone, so basically if there is a gap closing at 20 eV or 25 eV, by the time we reach at 100 eV, we will see that gap closing at 2-3 more photon energies. But that is not what is happening here. And this kind of anomaly was seen in the earlier experiments also. So, but that was used to explain that probably there is some anomalous reason for it, but it's three-dimensional. But then we thought that probably because neither in the, I mean, nor in this case, neither in this case, I mean, the gap closing is happening over a large photon energy range. So we thought that maybe because of some experimental geometry is giving rise to these things. So we carefully checked the experimental geometry.
Arindam has a question.
Yeah, Arindam, I was just asking that this Brillouin zone that you are talking about, this crossing of this Brillouin zone, this is in Z direction, this KZ direction Brillouin zone. Right?
Yes.
Yeah. Okay.
Yes.
Thanks.
Now, so this is the usual experimental geometry. So this is my sample, and the analyzer slit is along y-axis. So if we want to probe the gamma S direction, so that I have to align my sample in such a way that gamma S lies exactly along the y direction. But whenever we mount the sample, there is some misalignment. So instead of being parallel to y-axis or along y-axis, so it makes some angle with it. So that is some error. So that angle is called θ1. So this is an error angle. So this is an in-plane error. And also when we mount the sample, we want the sample normal to be along this analyzer slit axis. So we want to be it along in the direction of the slit. But because of the misalignment, the sample normal can make some angle with the z axis. So that is θ2. So these two are error angles. And we'll see that depending on the values of θ1 and θ2, we will get different gap trends. So basically the experimental geometry is giving rise to this gap. So this is an easier example to see. So in this case, you can see this Brillouin zone. In this case, we will be probing this direction. We'll probe this direction. So basically this direction now will lie parallel to y-axis. That is parallel to the analyzer slit. And gamma S, this direction will be perpendicular to y-axis. So see, so we have put our sample in such a way that gamma S is perpendicular to the analyzer slit or perpendicular to y-axis. And, and in this case, if we do the experiment, so what we are going to see? So that is the question. So you can see, so since the Dirac node lies at S bar point, so it has some momentum. It has some momentum, in plane momentum, and that is equal to 0.73 angstrom, the distance between these two. The distance between these two is 0.73 angstrom. And so the electrons corresponding to this node point will come out at an angle, because the in-plane momentum is given by this formula. Earlier I showed this formula. So now, this K parallel is 0.73, and this is with this dispersion relation, it is related to beta, the angle emission. So if I increase my photon energy, so kinetic energy of the electron increases and beta becomes small. And if I lower my photon energy, then kinetic energy becomes small and beta increases. So you can see this geometry here. So this is the in plane, out of plane error angle. So sample normal makes some angle θ2 with the z-axis, and your electrons corresponding to this Dirac cone comes at an angle beta. So if we use lower photon energy, the beta will be higher, and it would be much higher than θ2. And if we use higher photon energy, then the beta will be smaller and it will be less than θ2. So there could be three cases. So one when beta is greater than θ2, that is, we are using lower photon energy to probe it. So in that case, the electron corresponding to the Dirac node comes along this direction. So basically, and your slit is here. So basically your slit won't be able to intercept those electrons. So basically it will intercept something like that cone, and you are taking a cut which doesn't go through this apex. So basically this conic section will give you your Dirac dispersion in that case. So basically these red lines, so that these two disjoint hyperbolas you will see with a gap in between. So instead of getting a Dirac cone, you will see this thing. So at lower photon energy. And now as we increase the photon energy, beta becomes small. So the electron corresponding to the Dirac node now will be intercepted by this analyzer slit. So basically when beta equals to θ2, so in that case, so we will, the analyzer will take a cut through this Dirac node, I mean through this apex of the cone. So in that case, we will be able to see a perfect Dirac cone with no gap. And if we further increase the photon energy, the beta becomes smaller than θ2. So now the electron corresponding to the node will come along this direction. So in that case, again, you won't be intercepting, the analyzer won't take a cut through the apex. So it will take a cut at the right side of the cone. It will take a cut at the right side of the cone. So again, you will get two disjoint hyperbolas. So you can see how the Dirac spectrum in this geometry changes. So that we have plotted. So at lower photon energy, you can see higher gap. The black dots, the higher gap, and at some photon energy, the gap closes, and as you increase the photon energy, then gap increases. So, and this is the and over this photon energy, we have actually crossed 2-3 brilliant but there is only one gap closing, you can see. And this similar type of trend was seen by the earlier experiments. So this is taken from the earlier paper. So you can see they also got the same kind of trend. And we found that this trend, they got to get this kind of trend. So probably there was some this much of misalignment, this much, I mean almost 10 degree of out of plane misalignment in their geometry. So using these ideas of misalignment, we can fit our own data. So as I showed, we can have two misalignments, θ1 and θ2. And in both the cases, in both sets, we have these two misalignments. And this value of misalignments is not very unusual. Anyway, in this case, θ1 is actually higher. Generally, it is around 10 degree or less than that. So in this case, θ1 was higher, the in-plane your misalignment. But once you find out the misalignment and feed the data, you see, so it exactly matches with the gap trend that we see. So basically, if you try to find out the actual gap at the Dirac node, you have to subtract out these data points from this fit. And in that case, you will get almost zero gap. So basically, there is no gap actually. And this gap, whatever we are seeing, that is because of the sample geometry. So basically, these Dirac states are actually two-dimensional. There is no real variation there is no real variation with the photon energy. So this is one part of the experiment which shows that the Dirac states are two-dimensional. And since we acquired the spectrum at various photon energies and the resolution was very good, we could see some more surface states. I don't know if you are able to see it. So you can see, so DC1 is the Dirac cone at 0, 1, 0 surface. And there are other few surface states are here. So there are 5 more, we can see it. And there is another Dirac cone. It's actually not seen, but it's supposed to be there because these samples show twinning. I mean, that means, I mean, a bigger piece of crystal will have 2 crystallites which have 2 different terminations. I mean, a bigger crystal will have 2 crystallites side by side sitting, and one terminates on 0, 1, 0 surface and another terminates on 0, 1 bar 0 surface. And if your light falls on those 2 surfaces together simultaneously, then you can actually get the spectrum from 2 surfaces. And this has been found by earlier experiments also. So you have to optimize the sample carefully to get rid of those artifacts. So, so the DC2, I mean the Dirac cone on the 0, 1 bar 0 surface lies somewhere here. So just to make sure that these are actually surface states, I mean 2-dimensional states, and they are not dispersing with the photon energy. So we took the EDC curves at different photon energies. So these EDC curves are taken through this line, I mean at 0 momentum. So you can see there are few features which are non-dispersing. This is the intense feature, that is the Dirac cone, this one, DC1. And there are few other non-dispersive feature. I mean, their binding energy is not changing with the photon energy. So these non-dispersive features are there. 5 are there. So these are also the surface states, or maybe some 2-dimensional states. So then we studied the anisotropy of the these Dirac states.
Do you know what those states could be?
So actually these SS1 and SS2, you can see these states. Mm-hmm. So SS1, from the earlier band structure calculation, they found that this SS1 actually lies on 0, 1, 0 surface. And SS2, this one lies on 0, 1 bar 0 surface. So these two they have shown, but for these other surface states, they have not actually characterized through DFT, I mean on which phase they are lying. Because as I showed, I mean, because of twinning, simultaneously you can image both the surfaces, 0, 1, 0 and 0, 1 bar 0. So DFT calculation is needed to find out on which surface they are lying. But I can say these two, SS1 lies on 0, 1, 0 surface and SS2 lies on 0, 1 bar 0. Because earlier experiment also found out these 2 surface states. Okay. Okay. Now we address this attribute, anisotropy of the Dirac states. So anisotropic Dirac states have been reported in many materials, starting from Bi2Ac3, Bi2Te3, and there are other materials also, a lot of materials. So from these 2 spectra, so they are taken at orthogonal directions. So you can see they look very different. In this direction, it looks somewhat parabolic. But in this direction, it doesn't look parabolic at all. So the anisotropy is very clear. So to see it anisotropy much more clearly, we plotted the constant energy contours. So the binding energy positions of these contours are schematically shown here in this E and F in these 2 figures. The cut A is taken almost at the bottom of the Dirac state, bottom of the Dirac band, and cut D is taken at the top of the Dirac node. So cut B and cut C are near the Dirac node. So they are very close to the Dirac node. Now you can see one thing. So this so it has 2 contours. One is green contour, one is red contour. So green contours are coming from this green band, the up band, and the red contour is coming from the lower band, the down band. And you can see the 2-fold symmetry is very clear. The system has 2-fold symmetry. If you look at the crystal structure from B axis, it has 2-fold symmetry. So this twofold symmetry is very clear from all of these contour figures. And you can see that red contour here in cart B and the green contour here, the inner contour in cart C. So cart B and cart C are taken at very close to this Dirac point. So you can see they are almost circular. So basically that says that there is isotropy near the Dirac node. But as we go away from the node, there is anisotropy, or the twofold symmetry is very clear. And one more thing is that the outer contour, you can see it's not closed, because along this direction, this is the direction is the gamma dashed S gamma dashed. So in this direction, so you can see in this direction, the Dirac bands merge with the bulk band. So basically they don't close the contour in these two directions. So these observations, so now these observations are also confirmed from the derived dispersion. So these dispersions are determined from the energy distribution curves. So this is the dispersion along one direction where it looks somewhat parabolic, and this is along the perpendicular direction. And the corresponding spin splittings are plotted in these two figures. So in this direction, you can see the, in this gamma S gamma direction, so it doesn't look parabolic, some nonlinear dispersion is there, and correspondingly you can see the spin splitting also varies nonlinearly with the momentum. But along this direction, gamma dashed S gamma dashed, so it looks somewhat parabolic, and the energy splitting is linear. So now,
can you find from this some sort of VF as a function of theta? Is it possible to find isotropic Fermi velocity?
So this actually doesn't lie at the Fermi level. You can see it lies far below the Fermi level, but you can see, what is the velocity of these electrons near this?
Let me rephrase. Not the Fermi velocity.
Yes. So actually, we plotted it out. We fitted this, fitted it near this Dirac node, and we found the velocity as something like 8 into 10 to the power of 4 meter per second.
Okay.
And the graphene velocity is 1 into 10 to the power of 6.
Yeah, but that's in one particular direction, right? I'm just saying, if you're changing your direction, you should be able to see how far V changes.
So actually near the node point, we have isotropy. So near the node point, we will have velocity same along every direction. But
I see.
So because of this isotropy, you can see, these two dispersion matches here near the node point, they almost overlap.
Okay, got it.
So, so now we try to derive a Hamiltonian so that we can fit all these things. So the Hamiltonian has your time reversal invariance. So it has to satisfy this relation, this constraint, the time reversal constraint. And if you look from the B axis, so it has a C2 symmetry only. So the Hamiltonian has to respect this condition. So using this, we can write down a model Hamiltonian, and this is a constant, and these are the mass terms. These will give rise to the different mass terms, and alpha, gamma, delta are the first order terms, and these are the higher order terms. And we have seen that there is some isotropy in the system. So that's why we set these two masses along x-axis and y-axis as equal. So using this Hamiltonian, we perform some fitting, and we find a considerably good fitting. This is the dispersion along one direction. The dispersion along other direction we didn't fit because the number of data points were too less, but we fitted the spin splitting along that direction, and this is the spin splitting along this direction. So from this fitting, we can see these are the parameter values. And so there.
Can you go to the previous slide?
Mm-hmm.
Yeah. So these terms are Rashba terms or what?
This one is the Rashba term. This one is the Rashba term alpha, and this one is the Dresselhaus term. this, if you plot the spin structure of it, spin texture of it, you will see that, I mean, it gives rise to usual Rajba like spin texture.
Yeah.
And this one gives rise to a your Dresselhaus spin texture.
And this kx square, this other QSRT, these are
these are the higher order expansions,
higher order expansion.
Higher order terms.
And this theta kx ky is
theta kxy, it will give nothing, but it will change your mass term along different directions. So if you take along k, let's say if you are taking considering the Hamiltonian along some particular direction where kx equals ky.
yeah.
So basically then it will become your kx square. So basically it goes, it will get added to this term. So basically it will give rise to different mass term.
I see. So is this Hamiltonian like well known or like?
No. I mean,
yeah. Where do you get this Hamiltonian?
So basically you have to write down the terms which basically satisfy these conditions.
I see.
So because these systems has very less symmetry, these two symmetries, that's why, I mean, it was possible for me to write it.
Yeah.
Otherwise it requires, I mean, great knowledge of group theory to write down a Hamiltonian. It has only these two symmetries.
I see. Great. Yeah, go on. Yeah.
So using those, I mean, so from the eigenfunctions of those Hamiltonians, we can fit the dispersions and all these spin splittings, and from there we can get the.
Arindam, can you just go back? Sorry to bother you.
Yes,
previous slide. This
Mhm.
alpha, gamma, and delta are the linear terms. Alpha is
Yes,
the alpha, and gamma, delta are different Dresselhaus, and Q R S T are cubic term. Okay, so now can you go to the next slide?
Mhm.
I was just trying to figure out. I see. So some of your cubic terms are very large and some of your cubic terms are very small.
Yes, zero, almost zero.
Right? So
Yes.
does that tell you something more than your symmetry? There's like something about the origin that, you know, the alpha Rajba is finite, for example, but I'm guessing delta and gamma. Sorry, alpha and gamma are both finite.
Both finite, I mean, we cannot put them together. We cannot consider simultaneously, they cannot be non-zero, because then I have seen that they breaks the isotropy near the node point. So if I put both of them non-zero, then the isotropy near the node point is gone. So either of them can be non-zero.
Okay.
And
alpha is non-zero and
so
delta to be zero. Does that tell you something about the microscopic origin of such terms?
So that we actually spent some time on it, but we couldn't figure out, I mean, how these higher order terms are coming from it. Okay. I mean, we just see it, I mean, as a parameter, we just found it out, but what the physical significance of it or what is the microscopic origin of it, we really don't know that thing.
So this Rajba term is non-zero and Dresselhaus term is zero or not?
Because these are the surface states, and at surface we know that, I mean, the spin texture is always Rajba-like. So if you take alpha as 0.37 and gamma as 0, or either you take gamma as minus 0.37, alpha as 0, so both will give rise to the same contours. There is identical contours. But if you try to plot the spin texture of that thing, so then you will see that when your alpha is non-zero, so it gives rise to your Rajba spin texture. But if you take gamma as non-zero, it will give you a Dresselhaus spin texture. Yeah. And at the surface, we know that there is always Rajba splitting is there, the Rajba-like spin texture. So we think that gamma is 0 and alpha is non-zero. So,
by the way, you are almost closing in on 1 hour.
Oh.
So yeah.
So can I get 15 minutes? Because I'm almost finished. Graphene, then I'll
maybe you can just tell us the main
main things I'll tell, because we are currently working on it. It's not completely finished, so I'll be able to tell it in 10 minutes, I guess. So basically, so these are the parameter values we found, and you can see this is the spin texture of it. If we plot it out, spin texture we can get, and also this spin is completely lying in plane because the Hamiltonian had no sigma z term. So basically there is no out of plane spin components. So basically that's coming from the symmetry of the system, but Pi2AC3, Bi2TE3, they have large out of plane spin component. But here, because of the symmetry of the system, there is no out of plane component. So from there, so basically, so this is the anisotropic nature of the system. And then we went on to map out the whole band structure of the system. I mean, these Dirac states. So basically, varying the tilt angle, we got different spectrum this set of spectrum by varying the tilt angle, and from there we can get the dispersions. And if we plot it together, so this is the thing you can see. This is the derived dispersion, and you can see there are two saddle points here. One is here, another is here. So basically, if you see in this spectrum, the position of the saddle points are here. So these saddle points gives rise to the van of singularity in the density of states. And if we experimentally we found out the density of states, and we get a hump here. The hump is because of the resolution limitation of the experiment, and also due to the large energy step of the sampling. So if we get a hump-like feature here, and also from the derived Hamiltonian, we can see there are two singularities are there. So this one is experimentally seen, and this one probably some artifact of the Hamiltonian, because this singularity comes from another saddle points, which sits here at the top of this dispersion here and here. So that could be some artifact, but there is saddle point van of singularity in these states, but what it means physically, we have not been able to understand it. We are still working on it, whether this is a trivial property of the system or it means something for it. So we don't know it yet. So with this, I'll conclude. So in this study, we can unambiguously establish the two-dimensional nature of the Dirac state, and we could see several other surface states. And we found that the higher order spin orbit coupling terms has to be taken into account to explain the observation. And also the importance of the experimental geometry we can see. I mean, the experimental geometry has to be carefully analyzed before interpreting the data. And we found out the saddle point van of singularity, and further work is going on to understand the implications of this feature. And with this, I'll end the first part and I'll go to the next part. So this is on graphene. So we know that single particle picture of the graphene gives a linear band dispersion. You see the schematics. The outer cone is given by the single particle picture. But as we introduce the electron-electron interaction, and that then the linear spectrum deviates and it becomes more curved. So this inner cone we get as a band structure when we have a large electron-electron interaction, and that happens when we have Fermi level lying very close to this node point, because at that time the carrier density in the system decreases, so we have less number of carriers for screening, so the electron-electron interaction increases. So as the Fermi level go towards this node point, so the electron-electron interaction increases, the band structure deviates more from this linearity. Now these for the ARPES purpose, for the ARPES studies and for other studies, this graphene has been prepared on many substrates. You can grow it by thermal decomposition of SiC, and then you can further anneal it in hydrogen atmosphere or fluorine atmosphere to intercalate hydrogen or fluorine. Or also you can, this can be grown on, I think, nickel substrates and copper substrates also. So in our studies, we have grown it on SiC. So I'll just give you the background of a little bit of the earlier studies. So this is one earlier study where this is the spectrum they found. And in their case, they also prepared the sample by thermal decomposition of SiC. So here, this was the structure of the sample. You can see this is the top layer, carbon layer, which is actually the graphene layer. And the second carbon layer, that is a buffer layer. So it is connected with the substrate through these dangling bonds. So here, and we have this similar substrate in our case also that I will show. So in this case, you can see there is some anomalous intensity region here. I mean, the spectrum doesn't look perfectly conical. So and they also found out that this intensity here is non-dispersive. It's basically a straight line. It doesn't vary with the energy doesn't vary. There is no K dispersion of this intensity. So from these, they found out that they theorized that basically the gap opening is there. So basically these are the two bands, and in between there is a gap, and the gap value was around 250 MeV. And this intensity is because of some anomalous reason. So they were not able to properly say the reason behind this intensity. And this is another set of experiment done by another group. So this was done on a different sample. I mean, that was also prepared by thermal decomposition of SiC, but here the sample was intercalated with H. So basically there is one single layer of carbon, and that acts as a graphene layer. And these dangling bonds are satisfied by the hydrogen. So here you can see the band structure is not is composed of two cones here. So basically this cone, or you can see, so basically the upper cone, that is your actual hole band, and the lower cone, you can see there is another cone is there. So that lower cone is because of the plasmaron formation. So you can see here the schematics of it. And this and from theory it is known that not all plasmons can give rise to plasmaron. Only the plasmon having group velocity equal to the bare band dispersion can only couple to it. So basically this is the bare band dispersion. So the only this plasmon has the same group velocity as this, so it will couple to this whole band, and it will give rise to the plasmaron. And you can see, so this is theoretically calculated. So you can see the green, so this yellow line is your bare hole dispersion. And you can see one thing. So this is the cross section region of these two Dirac cones. So this is the diamond region. Above this diamond region, your bare hole dispersion is much more intense, and below this diamond region, your this plasmaron band is much more intense. So using this idea, they said that this group said that, so even in this case also we have this similar picture. So here what happens is that these wings of these plasmaron bands are much more suppressed, but this upper band is seen and this lower band is seen. And this anomalous intensity, whatever we see there, is because of this region. So because of this diamond region. So now we will show our studies. So this is our dispersion that we found out. And now if we take a EDC and fit it, so we'll see that there is a gap opening is there. It can be fitted with two peaks, and the gap will come out as 250 MeV, like the earlier reported thing. But that is not correct, because you can see the bands are overlapping here because of the low momentum resolution. So taking EDC and analyzing this spectrum itself is not a good idea. So basically we can acquire the spectrum in such a way by varying the light polarization, and because of the matrix element effect, we can individually image these two bands, and we analyze these two bands individually. And from these two spectrum, we get the dispersion. And you can see the anomalous intensity region which lies here, that is actually dispersing. But here, if you look at it, it doesn't disperse. So these two spectrum we have overlaid on it, and you can see. And this has been done for another two sets of samples. So these are boron doped graphene, and they have lower the Fermi level. So the Dirac point lies close to the Fermi level here. So you can see, in both of these cases, both of these two samples, you can see there is the anomalous intensity region. So there is dispersion. So there is probably no band gap opening is there. Now, if we compare these three, so I'll skip these things. So if you compare these three figures, the three dispersion, this is the pristine one, and these are the boron doped one. So this is highly doped sample, and the carrier density is higher in this blue, and the carrier density is lowest in this green. So if we plot it together, we can see, so there is deviation from linearity. If you just draw an arbitrary straight line here, you will see these bands are curved. So this is also theoretically very well known, and the curvature is more as the carrier density decreases, because the Fermi level lies close to the Dirac node, and the electron-electron interaction increases. So this has been shown by earlier studies also. Now, if you take these two spectrum, this green one and the pink one, and plot it together, you can see for the lower doping, as we decrease the doping, you can see the band is more curved near this node point. So it becomes much more narrower. So using these observation alone, we can say that probably there is no plasmaron in our systems, and also there is no band gap, because as we lower the doping, this band becomes much more narrower, and because of the finite momentum resolution, the intensity from these two bands, the RPS intensity from these two bands will overlap much more. So basically your anomalous intensity region will increase. So as you lower the doping, the anomalous intensity region is increasing. And if you say that region is related to the band gap, so that is not correct, because earlier it was said that this band gap is coming because of the sublattice symmetry breaking, because I showed that there are two carbon layers. So basically there is AB stacking between these two carbon layers, and because of that the sublattice of the top graphene layer is broken, sublattice symmetry. And so we do not expect that with doping the sublattice symmetry broken will be the same. We do not expect that the gap should increase, I mean, with doping. And also if we lower the your density, carrier density in the system, so the plasmon energy also decreases, because it goes as root over of n. So the plasmon which is able to give rise to this plasmaron particle has lower energy. So in that case, so that the anomalous intensity region will decrease, because the width of the anomalous intensity region depends on the your plasmon energy. So in both these cases, we see that as we lower the doping, either the anomalous intensity region should remain constant if it is coming from a gap, or it should decrease if it coming from the plasmaron. But here we see that it should actually increase because of the low resolution of the angle resolution. So it should increase. So from these we can conclude that there is no band gap, and also there is no plasmaron in these systems. And these are coming because of the electron-electron interaction on the system, and also because of the low resolution of the analyzer. So with this, I conclude our study. And I want to thank Professor Tamizawalan Ramakrishnan for the BIPD samples, and Professor Martin Wenderat's group for the graphene samples, and Dr. Dennis Valik and Sangeeta Thakur for performing experiments on BIPD and graphene samples, and for useful discussions with Dr. Bahadur Singh.
Okay, let us thank Arindam. And are there questions from the participants? Yeah. If anybody has a question, they can raise hand. So Arindam, I had a couple of questions. If you just go back to the graphene. So what is your energy resolution of your experiment here?
Energy resolution here is around 15 MeV.
15.
10 to 15. 10.
So now, normally you should also see a lot of puddle physics when you come closer to the Dirac point, right? The formation of charge puddles and so on. And typically people get a scale of maybe 50, 60 MeV for those kind of non-uniformities. You know that because of Coulomb interaction and lack of screening, you just form what you think as charge neutral just goes into locally regions of positive and negative charges. Okay.
Okay.
But here you do not seem to see any. If I mean, in most of those cases, I thought what they were missing was that there is puddle physics near at low energies, and so at low energies, you know, momentum is not even a good quantum number because you have inhomogeneous samples in terms of local density. Okay, but you seem to be saying that essentially you don't see any signature of puddle physics at all, even at
No, because all the earlier samples also, you can see here also. So those kinds of physics are not there in their samples also. So it's just the curved dispersion.
Yeah.
And also the actually the problem is that in our samples these experiments were performed at very high temperature, at room temperature. So the resolution is not very good actually.
So you have to
So and the sample doesn't survive for long at that temperature.
yeah.
So
Go down in temperature.
so that probably uh, so
So any other questions from anybody else? Vikram, you have any questions? I don't see any questions. Kalodar, if
No,
you
I'm good.
have any
I'm good. Sorry, I was turning on my mic.
sorry, I see.
Yeah, I'm fine. I
No,
don't
I
have
was going
questions.
to ask.
Actually, I'm on his TMC, so I know a lot of his work.
actually I have explained all these things to him.
Okay.
Yeah.
Kalabaran Maiti, Professor Kalabaran Maiti, Kalada, you want to ask something or?
No, it's okay.
Fine. Just making sure that
I know the work, of course.
I know.
But I don't think that these experiments are done at room temperature. I thought it was done at low temperature, and this particular graphene is done at a different beam line. So this one, the resolution was much better than 10 millivolt. So, but the Padul physics that you are talking about, I don't think that this is a concern here, because these samples are, studied before we did RPS. They have, they are good quality graphene, and we have also done some STM and so on to check things and so on. I think those things are not influencing. That's a comment maybe.
Okay. No, that's fine. Yeah.
Yeah.
Okay. So if there are no more questions, let's thank Arindam again. And